hands-on with freewheeling apps. A little over a month ago, I published a talk called Freewheeling Apps, which describes a way that I've been programming recently and that I've been advocating others should try for themselves. Um, that talk was very rehearsed, highly scripted, quite theoretical. Today I want to try something different, do something more spontaneous, um, focus on the lived experience of programming with these freewheeling apps, and hopefully it'll be more fun. Let's see. What are freewheeling apps? If you haven't watched that talk, I'll drop a link on it to it below this video. Um, but in brief, it's all these apps that you see on the screen, and I'm going to be using them in this talk. And the reason why I built these apps is in the software world today, apps abuse our trust, and apps have bugs. And apps have a tendency to grow increasingly complex over time. And the complexity is an opportunity to create more bugs and also hide potential sketchiness. So, what's the answer? The solution I'm exploring is forks, lots and lots of forks. Um, the hope is that if the source code is accessible and easy for anyone to read, then more people will take a look and uh, you don't have to trust an app. At least some people in a population will poke inside and make sure it's doing what it should and not doing anything it shouldn't. This is sort of the perennial promise of open source, but hopefully if we make it easier to look inside apps, then the benefits of open source will come through more easily. Um, I'm hoping that by creating a lot of forks, we can route around abuse. If an app starts to turn abusive, you don't have to drop using it entirely. You can just switch to a fork, which might be a smaller transition to make. I'm also hoping that forks will isolate the impact of bugs. If you notice that your app has a bug, maybe somebody's created a fork that fixes it, or somebody else had a fork which wasn't subject to that bug in the first place. I'm also hoping that a lot of our complexity in the world today in the software comes from using apps with a lot of features we don't use. And so if everybody just used forks of apps that had fewer features, that just had the features they care about, then the ecosystem as a whole will have simpler apps on average. So that's the world I want to live in. A little more quantitatively, just to rough orders of magnitude, I want a world where every app you think of today has 100 public forks that you can choose between. To get to those 100 public forks, we'd need to have 1,000 private forks where people try little experiments and some of them bubble up to become worth publishing. To get to 1,000 private forks, we need to have 10,000 programmers tinkering with these apps, looking inside them, seeing how things work, and coming up with ideas for changes they might want to make just for themselves in the beginning. To get to 10,000 programmers hacking on these little apps, we want a population of approximately 100,000 curious programmers, maybe wannabe programmers who are interested in seeing how things work under the hood. And to find those curious people, we need to have a population of 1 million people, not all of whom are programmers, most of whom just want to use the apps just like they do today. So that's the vision. The eventual goal is people who are not programmers. But at the same time, a lot of the proving out that I need to do is in this area of converting uh, people with some curiosity into programmers or taking existing programmers and teaching them about the internals of these very simple apps. And so this talk is going to be targeted more towards programmers. What do these apps look like? Let me first show you a big picture view of freewheeling apps. This is a list of all the freewheeling apps I've written so far. And I've arranged them from left to right in order of complexity. So the left side is less complex apps, the right side is more complex apps. And from top to bottom, the lines show you heredity. So they show you, I initially created this app called Lines, and everything else has been either a direct or indirect fork of that app. Let's start by talking, so Lines is an editor where you can edit text and also draw line drawings. Text is a simpler version of lines with just the text editing part. And view is a way to just browse a piece of text without having the ability to edit it. So that's some examples of forks. Out here on the right, we have some note-taking apps. And down here, this live template, this is where you start adding, these apps start adding the ability to edit their own source code live. And there's a few apps over here. And down here is the programming environment called the driver that is used to edit the source code for these apps. So that in itself is a freewheeling app. So let's start by looking at Poti here. Poti is a really, really simple blog reader. What you're seeing here is a list of markdown files that my friend Craig Sitaker has published on a Git repo somewhere. And so Cragen's a really wide-ranging person with a lot of diverse interests, and I enjoy reading his work. And I was inspired to create a client just to read his blog posts more conveniently. For example, here's a README for Hit This Repo. So this is his notebook just for the year 2022, and there have been 3 or 4 other annual notebooks before that. And here's an example blog post, is programming math. And so I can read it and I can hit reply and I can write comments. And maybe Cragen might one day, Cragen, please reply to my blog post comments. That's just a joke. And so on. So it's just a really simple app where you have blog posts and you have comments. Let's take a look at the source code for Poti. So this is the programming environment where you can make changes to Freewheeling Apps. And right now it's connected to Poti, which is the currently running app. And so you can do the usual things. I can make a change and you can see it happen live. I'm not going to do that today. What I want to show instead is, let's just look at the layout of this map of code. Everything is on a sort of infinite 2D surface. You can sort of pan around, zoom out. And if I zoom out to show the whole app, this is the boundaries of everything that's in this app above a certain level of abstraction. So this doesn't include the operating system. This doesn't include Lua. All this code is written in Lua. It doesn't include the Love game engine, which this is all built on top of. And it also doesn't include the core text editor widget that all my freewheeling apps use. But other than that, all the code for this particular app built on that, all that infrastructure is on the screen, as you can see in front of you. Now, I've laid it out in a certain way. This top few rows of definitions are data structures. Let's zoom in a little bit. So these are data structure definitions. And below them are functions. And I've arranged the functions roughly in columns that mostly use the data structures above them. So if you zoom in here, here are some functions that callbacks that describe what happens when you load settings, when the app starts up, how you save settings periodically or when the app shuts down. Here's initialization, and you can see that initialization initializes the file picker, which is the first screen you see in this app. Zooming out to other places, here's the draw handler, which draws a frame 30 times a second. Here are handlers for a keyboard press or a mouse press, and they have various helpers below them. Here are some things that happen on every frame, whether or not something was, there was an event or not. Here's the quit handler. So that's a very broad overview of all the things that this app cares about, the things that you need to program to build Poti. Let's look at a different app. Actually, before I do that, let me show you this again. So let's look at this fork, the picture of the forks. So we were looking at Poti. I'm going to go upstream a little bit and show you LuaML. So LuaML is basically a demonstration app. This is all hard-coded test data. And what this is showing you is a very, very simple browser-like model, something like HTML and CSS, with the ability to create little grid layouts. So this table, let's take a look at how it looks in source code. So I'm again opening up the source code. So here is on page is what you can think of as the HTML for LuaML. And it's all just syntactically valid Lua. And you can create boxes containing text, and you can create rows that contain other boxes in them, and you can create columns that contain boxes within them. And you can nest these infinitely. So you can have rows containing columns and the columns containing text boxes. And that's basically it. So zooming out on this app, again, there's this boundary where the data structures go on top. This is a very simple app, so there's really only one other data structure. It's called surface. And what's happening here is LuaML contains two functions at two different granularities called A and B. And these are sort of very core functions for this whole family of forks. A is fairly expensive work that needs to happen hopefully very infrequently. And what it's doing is translating the page data structure to the surface data structure. And so page is, like I said, our HTML, and surface is just a list of instructions, fairly high-level instructions for things to draw on the screen. And so A is going between them. Anytime the relationship between entities on the screen changes, we need to call A to refresh surface. B, on the other hand, it basically happens anytime the viewport changes. And so if I pan around, B is getting called all the time. But I don't need to redo all the work to translate page into surface just to change what I draw on the screen. So that's Poti. That's LuaML. So let me shut that down. Bad things happen if I ever open driver and start editing one app while another app is also running. So I have to make sure that I shut everything down. I only try to edit one app at a time. You can run multiple apps, but if you ever want to edit one of them, you should shut down all your other freewheeling apps as of now. So where were we? We saw Poti, we saw LuaML, which is upstream, and it's a lot simpler. And the source code follows a lot of the same spatial layout as Poti, but it's more sparse. And so you can see the difference between a complex app and a simple app. Let's look at another example. We're going to look at Snap, which is a different fork of LuaML. Now, Snap is, this is the app we just saw. We've been looking at this app all along. It's a little graph drawing program. And what it allows me to do is draw boxes and edges between boxes, type inside boxes with my editor widget, and adjust the width, delete edges, and that's basically it. Let's look at the source code for Snap. So again, the layout, the global layout should seem familiar. You've got data structures up top. You've got the various handlers, load, save, initialize, draw, keyboard press, mouse press, update, quit. So again, we're following the same idioms as all the other apps. One thing that's different is we have some green boxes, and these are tests. So the tests are currently passing, so you can see that the boxes are green. But if a test ever fails when I'm modifying my program, then everything goes red. And the borders go red, and this is handy sometimes if I'm modifying some unrelated function, and the borders going red warns me that something's wrong. And I can then zoom out and see precisely which box is turned red and go read the error message. Should be Y, but got X, and so on. Let's make it green again. So looking at Snap as a whole, the right side is fairly generic. It has the usual A and B and compute layout, which is called by A. The right side is more app specific. So a lot of the work here in Snap is happening in these callbacks for the mouse press and release. And so if you scroll down, we have various detectors for detecting when I click on a node or on an edge, for detecting when I'm on the border of a node, for detecting when I'm on the move bar above a node, for detecting when I'm on the resize bar to the right of a node, and so on. And it's all laid out. Again, what you see is all there is. What else have we got? I'm going to show you the driver program next, the source code for the driver. To do that, I need to first open an app. It doesn't matter what it is, because the driver won't start up unless there's an app it can connect to. Then I'm going to open the driver. And again, this is just what we saw just now. And now I'm going to open the meta driver. So the meta driver is connecting to the driver app. And if you take it all in at a glance, again, when I zoom out, what you see is all there is. It's a lot more complex. But again, it follows the same basic spatial layout. We have data structures up top, all across the screen. And we have callbacks for loading, saving. Initialization is somewhere here. Oh yeah, it was right there, right here. And then here's draw. Oh, these are keyboard press, mouse press. Here's mouse press. And here is draw. And update. There's no quit handler here, so it's a little different. You can see one test. I should probably have more tests. We have our usual, where is it? Yeah, here's A and B, which are translating from, this time, this particular fork doesn't have the hard-coded data structures. Instead, what we have is a list. Let's check. So here's definitions. Here's our, and definitions lives over here. It gets initialized when we load up the app, and that fills in all these little boxes on the screen all across the surface. Some of the major features here that cause the layout to expand outward are support for the zooming in and the zooming out, support for animation, I believe, is somewhere here. Here's animation. And all this happens both while initializing. You notice that there's a little zoom out and zoom in effect when you first load up the app. And it also happens on a specific keyboard press. Here's Control G. So when I press Control G, it's zooming out. What else? One little interesting bit over here is this function called drawTicks, which gets called on every single frame in the onDraw function. So you can see on drawTicks over here. And what this is responsible for is drawing these map-like coordinates on all the edges of the screen. And there's a fair bit of logic here to make sure that I never have too many ticks and I never have too few ticks, and that the resolution affects the frequency with which I'm drawing them. That's kind of fun. So that's sort of a very quick crash course on the source code for the driver itself if you want to edit it and make changes to it. I think that pretty much covers what I wanted to show. Let me summarize. So, like I said, the goal is I want to live in this world where there's a lot more forks, which in turn requires that the population's a lot more engaged with the process of programming and software development, which in turn keeps all the software creators honest because there's more accountability on their actions. Again, I don't expect everyone to be a programmer, but I do feel like we have to start on the side of the programmers. Those of us who know how to program need to be able to take on this power and responsibility of making our ecosystem more accountable. Thank you.